Welcome to this problem walkthrough. Today, we'll dive into problem number 1208, titled Get Equal Substrings Within Budget. This is an intriguing challenge that tests your ability to optimize substring operations within constraints. Let's explore the problem, its nuances, and how to solve it effectively. In this problem, you are given two strings, s and t, which are of the same length, and an integer max cost. The task is to determine the maximum length of a substring of s that can be converted to match a corresponding substring of t while keeping the total conversion cost within the given max cost. The conversion cost for each character is calculated as the absolute difference between their ASCII values. If no valid substring exists that meets these criteria, the output should be 0. The input includes the two strings, which have a length n ranging from 1 to 100,000, and the integer max cost, which can range from 0 to 1 million. The output will be an integer representing the maximum length of the valid substring. Now, let's look at an example to understand the problem better. Suppose s is ABCD and t is BCDF, and the max cost is 3. The output for this case is 3. Here's why: the substrings of s and t that can be converted within the cost of 3 are ABC from s and BCD from t. The conversion costs for each character in these substrings are 1 for A to B, 1 for B to C, and 1 for C to D. Summing these costs gives a total of 3, which is within the allowed max cost. The length of this substring is 3, which is the maximum possible in this case. Let's consider another example. Here, S is ABCD, T is CDF, and max cost is 3. The output is 1. To understand this, we calculate the conversion costs for each character. A to C costs 2, B to D costs 2, C to E costs 2, and D to F costs 2. Since the cost of converting any substring longer than 1 exceeds the allowed max cost of 3, the maximum substring length that can be converted is just 1. This demonstrates how the max cost restricts the length of valid substrings. Here's a third example where S is ABCD, T is ACD, and max cost is 0. The output in this case is 1. Let's break it down. The conversion costs are 0 for A to A, 1 for B to C, 1 for C to D, and 1 for D to E. Since the max cost is 0, only substrings with 0 conversion cost are valid. The only such substring is the first character, A, which matches it in T. This results in a maximum substring length of 1. Finally, let's review the constraints and edge cases. The length of S and T can range from 1 to 100,000, and the max cost can go from 0 to 1 million. Both strings will only contain lowercase English letters. When max cost is 0, only substrings with 0 conversion cost are valid, meaning the characters must match exactly. If S and T are identical, the maximum substring length is simply the length of the strings. When max cost is very large, the entire string S can be converted to match T. For single character strings, the substring length is 1 if the conversion cost is within max cost, otherwise, it's 0. Lastly, when the input size is at its maximum, the solution must handle these efficiently within the given constraints to avoid time limits being exceeded. To tackle the problem, we can consider two main approaches. First, the brute force approach, which is the most intuitive but also the least efficient. Here, we calculate the cost for every possible substring of S and check if it lies within the given max cost. For each substring, we compute the sum of the absolute differences between the corresponding characters in S and T, and we keep track of the longest valid substring. While this approach is simple to understand, its time complexity is O(n) squared, due to the nested loops required to evaluate all possible substrings. This makes it computationally expensive, especially for large inputs, and impractical for the constraints we typically encounter in LeetCode problems. On the other hand, a more optimized approach is the sliding window technique. This method avoids redundant calculations by dynamically adjusting the window size while keeping the total cost within the max cost. It's far more efficient, as it significantly reduces computational overhead by focusing only on the relevant parts of the substrings. To solve problem number 1208, we explored a few different approaches to find the longest substring that can be transformed within the given budget. The first method we considered was the brute force approach. Here, the intuition is straightforward: generate every possible substring of the input string S, calculate the cost of transforming it into the corresponding substring of T, and track the longest substring where the cost stays within max cost. Although this method is simple to implement, it is computationally expensive. Generating all substrings takes quadratic time, and for each substring, calculating the transformation cost requires additional linear time. This leads to an overall time complexity of n cubed, which is impractical for larger strings, such as when n is 10,000. Recognizing this inefficiency, we then explored an optimized approach using the sliding window technique. Here, instead of recalculating costs for every substring, we maintain a dynamic window of valid substrings. The goal is to expand the window until the cost exceeds max cost, and then contract it from the left to restore validity. This approach avoids redundant computations and allows us to process the string more efficiently. Using the sliding window approach, we achieve a significant improvement in time complexity. Each character in the string's S and T is processed at most twice, once while expanding the window to include it and potentially once more while contracting the window to maintain the budget. This results in an overall time complexity of n, making the approach highly efficient for large inputs. The trade-off here is that while the implementation is more efficient, it requires a good understanding of the sliding window concept to grasp how the window dynamically adjusts. We also considered an alternative approach using the prefix sum technique. This involves pre-computing a cumulative cost array, where each entry represents the total cost of transforming the substring from the start of S up to that point in T. Once this array is built, we can use binary search to efficiently find the longest substring within the budget for any starting index. While this method is efficient, with a time complexity of n log n, it introduces additional space for the prefix sum array and is less intuitive for those unfamiliar with binary search or prefix sums. After evaluating the options, we chose the sliding window technique as the primary solution for this problem. This method stands out for its balance of simplicity and efficiency. By dynamically adjusting the window's boundaries and tracking the running cost, we eliminate the need for redundant computations, which makes it preferable over the brute force method. While the prefix sum approach is also a viable option, it requires additional space for the cumulative cost array and involves a more complex implementation, particularly with the use of binary search. The sliding window approach, on the other hand, is both space-efficient and easy to implement once the concept of dynamically managing costs within a window is understood. The key insight here is recognizing that the transformation cost can be treated as a sliding window problem, where the cumulative cost can be adjusted on the fly as we expand or shrink the window. The real breakthrough moment comes from realizing that rather than recalculating costs for every substring, we can simply maintain a running total for our current window and adjust it as needed. When comparing the approaches, the sliding window technique stands out as the clear winner in terms of efficiency and simplicity. It achieves an optimal time complexity of n, without requiring additional space, making it well suited for large inputs. In contrast, the brute force method is highly inefficient with its n cubed complexity, which renders it impractical for all but the smallest cases. The prefix sum approach, while efficient with a time complexity of n log n, does require additional space for the cumulative cost array and is more complex to implement due to the use of binary search. By adopting the sliding window approach, we strike the ideal balance between performance and clarity, making it the most practical solution for this problem. The problem we are tackling, get equal substrings within budget, requires us to find the longest substring of two given strings, S and T, such that the cost of transforming S into T does not exceed a given budget, max cost. The transformation cost between characters at the same index is calculated as the absolute difference of their ASCII values. To solve this efficiently, we'll use the sliding window technique. We start by initializing two pointers, left and right, both set to 0, to define the current substring or window we are examining. Additionally, we maintain a variable current cost, which tracks the total cost of transforming the current window, and max length, which records the length of the longest valid substring we've encountered. The idea is to expand the window using the right pointer, calculate the transformation cost for each character, and add it to current cost as we iterate through the strings. If the current cost exceeds the given budget, max cost, the window becomes invalid. To fix this, we use the left pointer to shrink the window from the start, subtracting the transformation cost of the character at left from current cost and moving left forward. This process ensures that the window remains valid, meaning that the total cost stays within the budget. Once the window is valid, we calculate its length using the formula right, left plus 1. We then compare this length with max length and update max length if the current window is longer. After processing all characters in both strings, the value of max length represents the length of the longest valid substring, which we return as the result. The sliding window approach we've chosen is highly efficient because each character is processed at most twice, once when expanding the window and once when shrinking it, resulting in a time complexity of O(n), where n is the length of the strings. This ensures that the algorithm runs quickly even for large inputs. By dynamically adjusting the window size and maintaining a running total of the transformation cost, we can efficiently manage the budget constraints. Throughout the process, we continuously update the maximum valid window length to ensure we don't miss the optimal solution. The simplicity of the data structures used, including the 2 pointers and a few integer variables, also keeps the space complexity at O(1). When solving this problem, it's important to consider edge cases. If either string s or t is empty, the result is straightforwardly 0, as no substring can exist. If the budget max cost is 0, only substrings with no transformation cost, where the characters in s and t are already equal, can be valid. On the other hand, if the budget is very large, we can transform the entire string s into t. Another scenario to handle is when all characters differ significantly, causing the window to frequently shrink to meet the budget constraints. These edge cases ensure that the algorithm remains robust under all possible inputs. In terms of complexity, the algorithm's time complexity is O(n), as each character is processed only twice, and the space complexity remains constant at O(1), since no additional data structures are used. Let's walk through an example to solidify our understanding. Suppose the input strings are s equals abcd and t equals bcdf, with a max cost of 3. Initially, all variables are set: left equals 0, right equals 0, current cost equals 0, and max length equals 0. For the first character, right equals 0, the transformation cost is abs, ord, a, ord, b, equals 1. Adding this to current cost gives a total of 1. The current window length is right, left plus 1 equals 1, so we update max length to 1. For right equals 1, the cost is abs, ord, b, ord, c, equals 1, bringing current cost to 2. The window length becomes 2, and max length is updated to 2. Next, when right equals 2, the transformation cost is abs, ord, c, ord, d, equals 1, increasing current cost to 3. The window length is now 3, and max length is updated to 3. For right equals 3, the cost is abs, ord, d, ord, f, equals 2, which increases current cost to 5, exceeding max cost. To fix this, we shrink the window using the left pointer. First, we subtract the cost of transforming s, 0, reducing current cost to 4 and moving left to 1. Since the cost is still above the budget, we subtract the cost of s, 1, reducing current cost to 3 and moving left to 2. Now, the window is valid again, with a length of 2. However, max length remains at 3, as the new window is shorter. The result of this example is max length equals 3. This example demonstrates how the algorithm efficiently adjusts the window size to maximize the substring length while staying within the transformation budget. By dynamically balancing the current cost and using the sliding window approach, we ensure that the solution is both optimal and efficient. The combination of simplicity and robustness in this method makes it a powerful tool for solving problems with similar constraints and requirements. This Python solution leverages the sliding window technique to efficiently solve the problem of finding the maximum length of a substring within the given transformation budget, max cost. Let's walk through the code step by step. The function equalSubstring takes 3 parameters, 2 strings s and t of equal length, and an integer max cost. The goal is to maximize the length of a substring where the cumulative transformation cost does not exceed max cost. 1. Initialization. We initialize n as the length of the strings, left as the start index of the sliding window, current_cost to track the total cost within the window, and max_length to store the maximum valid substring length found so far. 2. Iterating over the string. Using a for loop, we iterate through the string s with right representing the end index of the sliding window. For each character, we compute the transformation cost of converting s, right, to t, right, using abs, ord, s, right, ord, t, right, and add this cost to current_cost. 3. Shrinking the window. If current_cost exceeds max cost, we shrink the window from the left by subtracting the transformation cost of S, left, to T, left, from current_cost and incrementing left. This ensures that the window remains valid. For updating maximum length, after adjusting the window, we calculate the current window size as right left plus 1 and update max_length if this size is greater than the previously recorded maximum. 5. Returning the result. Finally, the function returns max_length, which represents the maximum length of a valid substring within the transformation budget. This algorithm is efficient with a time complexity of O, n, as the right pointer traverses the string once, and the left pointer only moves forward. It ensures that we solve the problem with minimal computational overhead while maintaining clarity and correctness. This is the Java implementation for LeetCode problem number 1208, get equals substrings within budget. The logic mirrors the provided Python solution but is adapted to Java syntax. Key differences include the use of type declarations, Java's math.abs, for absolute values, and char@, for character access. The sliding window approach ensures optimal performance, and the code is structured to handle the problem's constraints efficiently. We start with the first example where S is ABCD, T is BCDF, and max cost is 3. The goal is to find the longest substring where the total cost of changing S to T does not exceed the given max cost. To begin, we initialize the variables. Left is set to 0 to mark the start of our sliding window, current_cost is initialized to 0 to keep track of the cumulative cost, and max_length is set to 0 to store the length of the longest valid substring. We then iterate through the string using a right pointer from 0 to n1. For right equal to 0, the characters are at ns and b and t. The cost of this transformation is the absolute difference between their ASCII values, which is 1. We add this cost to current_cost, making it 1. Since current_cost is less than or equal to max cost, we calculate the length of the current substring as right minus left plus 1, which is 1, and update max_length to 1. Next, for right equal to 1, the characters are b and s and c and t. The cost is again 1, so we add it to current_cost, resulting in a total cost of 2. This is still within max cost, so we update max_length to 2 by calculating the new substring length as 2 to 0 plus 1, which is 2. Now, for right equal to 2, the characters are c and s and d and t. The cost of this transformation is 1, so we add it to current_cost, which becomes 3. Since 3 is equal to max cost, we calculate the length of the substring is 2 to 0 plus 1, which is 3, and update max_length to 3. Next, for right equal to 3, the characters are d and s and f and t. The cost here is 2, so adding it to current_cost gives us a total of 5. Since 5 exceeds max cost, we need to shrink the window from the left. First, we subtract the cost of transforming S, 0, to T, 0, which is 1, reducing current_cost to 4. However, 4 is still greater than max cost, so we shrink the window again by subtracting the cost of S, 1, to T, 1, which is also 1, bringing current_cost down to 3. We increment the left pointer to 2 and calculate the substring length as 3 to 2 plus 1, which is 2. However, max_length remains 3, as it is the maximum length encountered so far. The final result for this example is max_length equals 3. In the second example, S is ABCD, T is ACD, and max cost is 0. Again, we initialize left to 0, current_cost to 0, and max_length to 0. For right equal to 0, the characters are at in both S and T. The cost of this transformation is 0, so adding it to current_cost keeps it at 0. Since current_cost is less than or equal to max cost, we calculate the substring length as 0 to 0 plus 1, which is 1, and update max_length to 1. Next, for right equal to 1, the characters are b and s and c and t. The cost here is 1, so adding it to current_cost makes it 1. Since 1 exceeds max cost, we shrink the window by subtracting the cost of transforming S, 1, to T, 1, which is 1, bringing current_cost back to 0. We then increment the left pointer to 2, making the window invalid for this right pointer. The maximum substring length remains 1. The final result for this example is max_length equals 1. In the third example, S is KRRGW, T is ZJXSS, and max cost is 19. As before, we initialize left to 0, current underscore cost to 0, and max underscore length to 0. For right equal to 0, the characters are k and s and z and t. The cost of this transformation is 15, so adding it to current underscore cost makes it 15. Since 15 is less than or equal to max cost, we calculate the substring length as 0 to 0 plus 1, which is 1, and update max underscore length to 1. For right equal to 1, the characters are r in s and j and t. The cost here is 8, so adding it to current underscore cost increases it to 23. Since 23 exceeds max cost, we shrink the window by subtracting the cost of transforming s, 0, to t, 0, which is 15, reducing current underscore cost to 8. We then increment the left pointer to 1. With current underscore cost now less than max cost, the length of the valid substring is 1 to 1 plus 1, which is 1. The maximum substring length remains 1. The final result for this example is max underscore length equals 1. To analyze the time complexity of this algorithm, we start by looking at the sliding window approach it uses. The algorithm iterates through the strings s and t using a for loop, where the right pointer moves from the start to the end of the strings. This loop runs n times, where n is the length of the strings, giving us a time complexity of O, n, for this part. Additionally, the while loop adjusts the left pointer when the current underscore cost exceeds max cost, effectively shrinking the window. Each character in the string is visited at most once by the left pointer, ensuring that the total operations performed by the while loop across all iterations is also O, n. Finally, for each pair of characters, the algorithm calculates the cost, which is done in constant time, O, 1, per iteration of the for loop. Since this happens n times, the cost calculation contributes O, n, overall. When we combine all these components, the for loop and the while loop together result in O, n, time complexity. This is because the total number of operations performed by both loops scales linearly with the size of the input. All other operations, such as the cost calculation and variable updates, are O, 1, and do not affect the overall complexity. Therefore, the total time complexity of the algorithm is O, n. Now, looking at space complexity, the algorithm operates directly on the two input strings s and t, which already occupy O, n, space, but this is part of the input and not additional space used by the algorithm. For auxiliary variables like left, current underscore cost, and max underscore length, the algorithm uses a constant amount of additional space. Since no extra memory is allocated for data structures proportional to the input size, the additional space complexity is O, 1. To understand the efficiency of this approach better, let's compare it with a brute force solution. A naive approach would involve checking every possible substring of S and calculating the cost of converting it to T. Given that there are n plus 1/2 substrings in a string of length n, and calculating the cost of each substring takes O, n, time in the worst case, the total time complexity of the brute force method is O, n cubed. In contrast, the sliding window approach avoids recalculating costs for overlapping parts of substrings. Instead, it maintains a window of valid substrings and updates the current underscore cost incrementally as the right pointer moves. This optimization drastically reduces the time complexity to O, n. In terms of space complexity, both the brute force approach and the sliding window method use O, 1, additional space, as neither requires extra data structures beyond a few variables. Now, let's break down the time complexity further by analyzing the best, average, and worst case scenarios. In the best case, where all characters in S and T are identical, the current underscore cost never exceeds max cost, meaning the while loop never executes. Here, the algorithm runs in O, n, time, as the for loop still iterates through the strings. In the average case, the while loop executes a limited number of times, proportional to the size of the valid window. This still results in O, n, time complexity because the left pointer and right pointer collectively perform at most 2n movements. In the worst case, if the cost of converting every character in S to T exceeds max cost, the while loop executes once for every character of S. Even in this scenario, the total number of operations remains linear, and the time complexity is still O, n. To mathematically prove the algorithm's time complexity, consider the following points. The for loop iterates n times, contributing O, n. The while loop, which adjusts the left pointer, also moves the pointer a total of n times across all iterations of the for loop. Thus, the combined operations of the for and while loops amount to O, n. Within these loops, the cost calculation and all other operations, such as variable updates, are O, 1. When we sum these up, the total time complexity becomes O, n, plus O, n, asterisk O, 1, which simplifies to O, n. On the space side, the algorithm uses only a constant amount of extra memory for variables like left, current_cost, and max_length. Since no dynamic memory allocation is involved beyond the input strings, the additional space complexity is O, 1. To start, one common mistake is misunderstanding the concept of the budget. Remember, the budget refers to the maximum allowable cost of the absolute differences between corresponding characters in the two strings, not the actual length of the substring. Misinterpreting this can lead to incorrect logic when determining whether a substring is valid. Another frequent issue involves incorrectly managing the sliding window. If the cost exceeds the budget, you need to shrink the window from the left, otherwise, you might overestimate the substring length. Efficiency is another key point to watch for recalculating the substring cost from scratch every time the window changes, as in a brute force approach, can result in a time complexity of O, n squared. Instead, you should maintain a running sum of costs. Lastly, off-by-one errors can trip you up, especially with zero-based substring indexing. Failing to handle edge cases, like empty substrings, can lead to incorrect results or runtime errors. Always double-check your indexing logic to avoid these pitfalls. Now, another important point is to account for edge cases. For example, what happens if the input strings are empty, all characters are identical, or the budget is 0? Overlooking these scenarios can cause your solution to fail unexpectedly, so handling them explicitly is crucial. From an interview perspective, this problem is an excellent opportunity to demonstrate mastery of the sliding window technique. This pattern is widely applicable to problems involving substrings or subarrays, so it's worth mastering. Interviewers also value how you optimize your solution. Transitioning from a brute force approach to an O, n sliding window solution reflects a strong grasp of algorithmic efficiency. Be ready to discuss the trade-offs of your approach, such as why sliding window is more effective here than using prefix sums, since it allows real-time adjustments to the window. Finally, always communicate your edge case analysis clearly with the interviewer. For instance, clarify how you'd handle scenarios where the budget is negative or the strings have unequal lengths before diving into implementation. Next, it's helpful to explore related problems that utilize similar techniques. For instance, problem number 209, minimum size subarray sum, involves using a sliding window to find the smallest subarray with a sum greater than or equal to a given target. Problem number 567, permutation in string, applies a sliding window to determine if a permutation of one string is a substring of another. Then there's problem number 424, longest repeating character replacement, which uses a sliding window to find the longest substring achievable after character replacements. Finally, problem number 1004, max consecutive ones 3, employs a sliding window to maximize ones in a binary array by flipping at most k-zeros. These problems share common principles, so practicing them can deepen your understanding of sliding window patterns and help you recognize variations in their applications. Finally, let's compare some alternative approaches and their trade-offs. A brute force solution involves iterating over all possible substrings, calculating their costs, and checking if they meet the budget. While this approach is straightforward to implement, its O, n squared, or worse time complexity makes it impractical for larger inputs. Another option is using prefix sums to pre-compute the costs of substrings, allowing for quicker retrieval. However, this approach increases space complexity to O, n, and may require additional effort to manage the prefix sum array effectively. The most efficient solution is an optimized sliding window approach. By expanding the window to include new characters and shrinking it from the left when the budget is exceeded, you can maintain a running sum of costs. This achieves O, n, time complexity while keeping space usage minimal, striking the best balance between speed and resource efficiency for this problem. Thanks for following along. We reviewed the problem, broke it down step by step, and explored an optimal solution. Don't forget, sliding window techniques are versatile tools for solving problems like this. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!